and I work here at Google as part of our compiler team. And this talk is just some discussion of what's going on in the GCC compiler these days, with some notes in particular on the work that we're doing in Google, but I'm also going to be covering work that's being done outside of Google. Please feel free to interrupt me at any time with questions or comments or screams of horror. And here we go. I think that everybody here knows what GCC is. But just in case, it's the GNU Compiler. It compiles that list of languages that you see listed up there. The project was started in 1987 by Richard Stallman, the founder of the Free Software Foundation and the starter of the entire GNU collection of code. I've made a little list of GCC releases over time. You can see that Richard released 1.0 back in 1987. And the most recent release was just a week and a half ago, 4.1.2. As you can see from this little chart, we managed to do 42 releases in the first 5 years, and 9 releases in the next 7 years, and 5 releases in the next 3 years. And since 2005, we've basically managed 2 releases, not counting minor releases. So as you can see, things are slowing down quite a bit. We like to think that's because we're doing more testing and it's becoming more stable over time. There's still a lot of changes going in, but we've changed the release process to be quite a bit more arduous to get through than it used to be. I personally started working on GCC in 1990, by the way, with GCC 1.34. And I haven't worked on it exclusively in the years since, but I have spent most of my time working on GCC and on the related tools. Here's a list of changes since 1998, the number of changes per year. You can see that it's quite an active project. There's a lot of active contributors to it. You'll see that the number of changes has dropped down in the last couple of years. That's mainly because we've shifted to a model of doing major development on branches. So from the point of view of this count, we'll do a lot of development on a branch that will come into the main line of GCC as a single change and only get counted once here. But as you can see, though, an active project, a lot of work going on it. People from a number of different companies contribute to GCC, not just Google, but also major contributors include Red Hat, SUSE, which is part of Novell, IBM, Code Sorcery, Specifics, and there's a lot of individual contributors at universities and the like. I haven't tried to break it down, and of course we have a number of volunteer contributors, and we were a Google Summer of Code project last year and will be again this year. So the first topic I wanted to talk about. There's been a recent major rewrite of the internal data flow framework within the compiler. It's actually still ongoing and hasn't been committed into mainline. Data flow is the word that compiler people use to track the association between when a variable is defined and when a variable is referenced. The existing implementation that we have in GCC was written in 1987 by Richard Stallman. Academic compiler research has proceeded quite a long time since that date, and we're revamping the infrastructure to be much more accurate and also to run faster. The result should be better optimization in the long run, as we are able to update some of our old code that's been around since the 80s and replace it with more modern code. I have a little example here to show what data flow is. Here's a simple program. You can see it assigns to a couple of variables, uses a couple of variables. Data flow tells us the definitions and the references. So what we're adding is the ability to, as you'll see, the numbers there refer to the line numbers. So as you'll see on line 7, we know that that J refers to the assignment made on line 2 and cannot possibly refer to the assignment made on line 4. This is a very simple example of the kind of knowledge that we're going to have in much more complex programs for the benefit of optimization. Here's.
When will we see sort of the results of that in a release of GCC ballpark?
This will be in GCC 4.3. As you saw, 4.1.2 was just released last week. 4.2 we expect to release, let's see, it's the end of February. I would hope it would come out in April or May, 4.2. We've already done a release branch for 4.2, and then this work is going into 4.3. Here's some more work going into 4.3. We are improving the warnings about invalid aliasing, and I'll explain that in a minute. Silvius, who's sitting right there, has done this work. Now you have to wave so everyone can see who you are. He works here at Google on the compiler team. And I wanted to mention that Danny Berlin, who is now at Google, is one of the major authors of the aliasing code in GCC. He's worked on that since before he came to Google last year. Now for our example. What aliasing means in the compiler is when two different pointers can refer to the same memory location, which of course is a very natural thing to have happen. It's how one typically uses pointers. But the interesting thing about aliasing is that the language standards for C and C++ specify that if you have a pointer of a given type, the standard says if you try to use that pointer to refer to an object of a different type, then that access is what compiler people call undefined behavior. Undefined behavior in the compiler means that the generated code can do absolutely anything. Compiler writers like to use hyperbole, like it could launch nuclear missiles, it could sell your house. In practice, what it means is that the generated code may jump to a random memory location, and you have absolutely no idea what's going to happen next. So what we have here in this program is you'll see that there's a pointer to int and a pointer to float. And we're going to cast the pointer to int so that it's a pointer to float, and then we're going to dereference that pointer to float. Now that's an example of undefined behavior because we are using a float pointer to access an int variable. So would anybody in this room who is not a compiler developer care to predict what this function will return?
Garbage.
That's correct. If you compile this with GCC today, it will return an uninitialized value. It will simply return whatever value happens to be in the return register. So don't write your code like this. A lot of people do write their code like this, we've discovered. Because, because before the language standard, this code might have been defined. It might have said something like return whatever the bits for 3 happen to look like if you interpret them as a float. That might have been a valid interpretation of this program. Most compilers historically, not recently, but historically would have done exactly that. They would have taken, 0011 and whatever that happens to be as a float, some very small denormalized number, and just return that. But modern compilers do not do that. Now, there's a reason they don't do that. And the reason is if the compiler knows that a pointer to float cannot alias a pointer to int, that is, if a pointer to float cannot point to the same memory location as a pointer to int, that means that the compiler can rearrange loads and stores of float pointers without regard to int pointers. And that permits the compiler to generate more efficient code. It permits the compiler to reschedule the code so that the instructions run in some order that's particularly efficient for the machine at hand. All of these things are increasingly important with modern processors. The ability to reschedule instructions is very important with modern processors. So compiler writers take advantage of the leeway that the language standard has given us to say, oh, this is undefined behavior. You can't possibly mean give me, the bit mask of 3 interpreted as a float. I don't know what you mean, but I'm just going to pretend you mean nothing. So since real code does actually work this way, especially old code, we found that it's desirable to warn people when they're doing this. GCC has not in the past implemented a warning, but Sylvius has implemented a warning. Here's an example of what it would say for this particular code. I'll just read that. Likely type punning may break strict aliasing rules. Object *f of main type float is referenced at or around line 5 and may be aliased to object I of main type int, which is referenced at or around line 1. So hopefully, programmers will be able to interpret this to say, well, something's wrong here. And they will fix their code. By the way, the correct way to write this code would be to use a union. The language standard doesn't actually support using a union, but GCC and all other compilers do in fact support that, so that there is a way to do this kind of reinterpretation of the bit mask value. The other correct way to write this code, of course, would be to rewrite it, since it doesn't really make any sense. But any questions about aliasing? Very good. So it seems like a pretty simple change to add this warning, but Sylvius has worked on it for a few months now. It's actually pretty complicated. You'd be surprised. The next one is a somewhat similar case, which I've been working on. This is another example of compiler undefined behavior, is that if you get an overflow of a signed integer value, the language standard says that that is undefined behavior. It doesn't say it's going to wrap around the way you might think because you remember how 2's complement numbers behave. It says absolutely anything could happen. And the compiler takes advantage of that. For example, this might be a simple loop which attempts to test how many bits there are in an int. As you can see, it simply adds, it doubles the int, and it keeps looping as long as it is positive, because as we all know, when you double, eventually if you keep doubling a positive number, you're going to wind up with the most negative number. That's what's going to happen in practice. So here we see an example of signed overflow, because you know that overflow, that is overflow. When it overflows past a positive number to become negative, that's signed overflow, and that's undefined behavior again. So if you compile this with the current compiler, does anyone care to predict what's going to happen with this loop? Somebody must have a guess. You're on the compiler team. GCC will happily turn this into an infinite loop.
So did previous GCC versions, did they terminate as you would expect for a signed int?
Yes. Yes, turning this into an infinite loop is a brand new and exciting feature in GCC. Once again, you might sort of start to think to yourself, I don't really want this to happen. But there is a reason for this again, and the reason is when GCC knows, when it knows that your loop indexes cannot overflow, it can do a much better job of unrolling your loop and of determining the number of iterations that your loop will actually execute, which also helps with unrolling, helps with inlining. Adding this feature, on various standard benchmarks gives us significantly improved behavior. Very few people write this sort of loop, but of course some people do. So when we rolled this out in the GCC 4.2 release snapshots, some people tried running it and they said, wow, my program really takes a long time. This GCC release is not very good. So I have implemented warnings, which will become part of GCC 4.2. Two new options. One option is -f strict overflow. That's a new option which tells GCC, yes, you may assume that signed overflow is undefined behavior. And as you can see, turned on at 02. And the other more interesting option is now there's a warning, W strict overflow. You can I've had to make a range of levels because there's a number of very innocuous optimizations which GCC makes, which assume that signed overflow is undefined. I forgot to put in an example of it, but an example of that would be something like optimizing I times 10 divided by 5 into I times 2. That optimization can only be done if you assume that signed overflow is undefined, because I times 10 itself might overflow and might turn into a negative number. We've done that optimization for a long time. We've only done this loop optimization as of GCC 4.2. So with this new option, you will get a warning, which will basically say GCC assumes signed overflow is undefined when optimizing I greater than 0 to 1. Moving on. We've been working on a faster preprocessor. A while back in GCC 3.0, we integrated the preprocessor and the compiler proper. That is, we used to have two separate programs, one which was called CCCP, which was the C preprocessor and did not refer to any former country, and the other was the compiler itself, which took the preprocessed code and generated assembly code. The new preprocessor was faster when you were doing an ordinary compile, because instead of being a text-to-text transformation, it actually tokenized the input into a series of tokens which the compiler could then process directly. However, the new preprocessor was slower when preprocessing. And mostly everybody was fine with that because not very many people ran the preprocessor by itself. But more recently, programs like Ccache and distcc separate the two steps. What Ccache does is it runs the preprocessor and then builds essentially a hash table from the preprocessed input to the generated object file. And it just, if it's already compiled that preprocessed input, then it returns the object file directly without running the compiler. Thus, it's a compiler speed-up mechanism for projects which have a lot of header files, in which modifying one header file doesn't necessarily change the generated code. This is pretty characteristic of large projects written in C. distcc is a similar project. By the way, these are not associated with GCC per se, although they're written to be used with GCC. distcc is a program which distributes compilation across a bunch of machines. It again does the preprocessing on the local machine, and then it picks up the preprocessed codes and sends it to one of a set of servers where the actual compilation is done. So if you are lucky enough to have 10 or 20 or 2,000 machines to run your compilation, then distcc will let you run parallel makes much, much faster as the code is shipped out. But the preprocessor is slower. We've sped it up, in part by not tokenizing, by going back to the way it used to work when you give it a special option. And that was implemented by Ollie Wild here at Google. And I also did, it was mostly done by Ollie Wild. I also did some work on it myself. And the next thing I wanted to talk about was a bunch of changes we're making for the next update to the C++ standard. I'm sure that many of you are still just getting used to all the features of the last C++ standard, but there's another one coming out. They're calling it C++ 0x in the hope that it's done by 2009, but I was just talking to Lawrence here, who's actually on the committee, and it looks like it's going to be more like C++ 0a or 0b. It's just, there's apparently quite a long lead time in getting these things actually approved. I don't know how many of you remember the ANSI and ISO C standardization process, but I remember that took something like 3 years after it was finally finished to finally get approved and turned into an official standard. Despite that, we already support options. We don't support most of the features, but we do have some features already implemented. You can select C++ 0x as a standard. There's a warning option which says whether or not your code is compatible with C++ 0x as defined so far. several new keywords are being added. So the main effect of the warning is to say, oh, your variable name is going to be a keyword when C++ 0x comes out. We've implemented static assert, which is pretty much what it sounds like. It's a function which checks at compile time that some condition is true. We've implemented a very exciting feature in the past. Here, you had to have a space. So that space is going to be optional in C++ 0x. This turns out to change the meaning of some valid programs, which involve the right shift operator. So that's also warned about if you give the warning, if you happen to be so peculiar as to write one of the programs which would be changed. We also have an implementation of variadic templates in which you can write a template with, a variable number of parameters. I'm not quite sure why that's useful, actually, but I'm sure there are some good uses for it. All part of doing more of your compilation at compile time, I guess. More of your computation at compile time. This work hasn't been done at Google. It's mostly been done by Doug Greger at the University of Indiana, and a number of other people have contributed. And we have 3 members of the standardization committee here at Google, whose names are right there. And Lawrence is sitting up front there. Any questions about what's coming down the pike here? No. Parts of it, some of it's pretty scary. You thought that C++ was a complicated language before. It's just a new layer of complexities being put into it. Now something that's a little more in the future. This is not going to be in 4.3, but it's going to be rolling out, I hope, in 4.4. We're going to see this is whole program optimization. This is a feature that several compilers, several non-free compilers have had for a few years now, like IBM's XLC and Intel's ICC compiler, and I think also PathScale have this feature. Basically, I'm going to describe what we're going to be doing as part of GCC, at least. When you compile code, it's going to compile not just into object code, but also into an intermediate representation, which will be stored in the object file itself, if you use the appropriate options and so forth. Then at link time, instead of simply invoking the linker with the object files, the compiler will run. It will grab the intermediate representation out of the object files, and it will proceed to attempt to optimize the whole program at once. And I've put some examples up here of things that we can do when we do that. The most obvious one is that you can write your function in one file and then have it inlined into a function written in another file. The only way you can do that today is to put it in a header file, which, of course, is not always desirable. It breaks your modularity. But with this feature, we'll be able to do that inlining across .o files, which is also convenient for if you're using programs written in 2 different places, like some library that's distributed. We'll be able to, with whole program optimization, we'll be able to, in many more cases, know every single caller for a function, which generally is not the case today. We'll be able to take advantage of visibility attributes to say, we now know everybody who could call this function, and that gives us a number of advantages. We can actually change the calling convention for that function to pass more arguments in registers or fewer arguments in registers. That we can say this function no longer has to save all its registers. That can be a big help for a small function. It can make a huge difference for some types of code. Similarly, we can actually clone the function. We can say, looking across the whole program, for some reason, this function is called 100 times with a first parameter of 10. So let's just make a copy of it. Let's say now we no longer have to pass that first parameter. Let's make that first parameter 10. Let's do constant folding through the function. We'll get a more efficient version of the function. It'll be called more efficiently. We can also do much improved alias analysis when we can see the implementation of the function. We can say, originally, this function might have changed these global variables. Now that I can actually see the value, I know that it does not change these global variables. I know that it does not dereference these pointers. I no longer have to save everything into memory before I call the function. So alias analysis, which I talked about earlier, might seem like a somewhat abstruse topic, but it's actually very key for a wide range of optimizations within the compiler. This project within GCC is called the LTO project. I forgot to write that up there, which stands for the Link Time Optimizer. I've written the names of a number of the people who are working on it, and as you can see, we've got a couple of people at Google working on it as well. This is a big project. It's not, part of it, of course, is the simple matter of writing out that intermediate representation, but we also have to, the traditional problem with whole program optimization is that you run your compiler, it runs around to all the object files, it sucks in all the intermediate representation for your program. The compiler then uses up 4 gigabytes of memory and crashes because it can't alloc any more space. So in order to make this work, it's very important to optimize the memory usage of the compiler and to compact the intermediate representation. And that's what people like Sandra and Aldi are working on. In order to, just making GCC more memory efficient. This is going to be, if we can make this work, and this is still obviously experimental, if we can make this work, I think it'll be a very huge step forward in optimization for real programs. And as I say, we hope the first implementation will be in 4.4, although we'll have to see if we continue our current release schedule. 4.4 won't be out for another year at least, so that does give us a pretty good chance. Any questions about this?
If you clone the functions, will it be like a mangled name or something like that, so the GDB knows where the hell it is?
Yeah, well, GDB will know where it is because the debugging information will point you right back to the same source code lines it had before. But will it be a mangled name? Yes, it will certainly be a mangled name. GDB will have to be taught what that mangled name actually means. We don't currently have any mangling scheme which can represent this, so we'll be making something up for it. This is actually my last slide. These are additional projects which people are working on. Using GCC as a just-in-time compiler for virtual machines. This is, as I'm sure many of you know, virtual machines like, for example, the Java virtual machine, which executes Java bytecode. The most efficient virtual machines these days actually say to themselves, look, I'm about to execute this function for the 100th time. Instead of interpreting this bytecode, I'm going to compile it instead and simply execute the machine code every subsequent time that I run this function. Diego is working on the steps required to make GCC be a compiler which can be used for virtual machines built out of fully free software. And similarly, the CIL is a C intermediate language, which I believe was defined at Microsoft. Roberto Costa is working on having GCC generate that intermediate language. These, as I say, are longer range projects. And those are the topics I had to talk about today. I hope this has given you an overview of what's going on in the compiler community. It's a very active community, and we always welcome people who are interested in compilers or just interested in anything really to help out. The website, which I probably should have put up here, is gcc.gnu.org. I should also add, as I say, we have a compiler team here at Google of some 9 people, I guess. We don't have our own private version of GCC. We do have some local patches, which we're continuing to try to contribute back to the main branch of GCC, but mostly we're just a active member of the wider GCC community. And I'll take questions on any topic, yes.
Profile guided optimization. I know compilers that use that, and I heard that GCC was incorporating that.
A question about profile-guided optimization. Good question. GCC has had profile-guided optimization for quite a long time, although I'm not sure how many people are aware of it. You compile your code with the -f profile generate option and your optimization options or whatever. Then you run the code several times using some representative data set, and it will write out I think it's a gcov.out file. Then you compile it will write out actually a set of those files. Then you compile your program again with the -f profile use option. And this time it will look at the profile information and it will use it to optimize the code. The kinds of profiling information which it does is branch prediction. It will record which way branches go, which will let it rearrange the code to get better cache locality. It will also do value prediction, which it will use for some very specific cases. For example, for calls to memcopy, it will record the values that are passed as the size of the buffer to be copied. And if it turns out to be helpful, if some more than 50% of the calls at some particular call site are always with the same constant third value, then it will add in a condition. If length is this, then it will do the copy inline using all the knowledge it has about the alignment instead of calling out to the library function. And you're right, I didn't put it on the slide, but there are improvements there being done by Alde Hernandez and Jan Hubica. And they are working to increase the number of cases which we take advantage of profile generation. Also, Sungbei Park here at Google has been working to make the profile feedback more flexible.
So a follow-up on this actually. Do you have to use exactly the same file and binary, or is it sufficient that you're sort of linking in some of the libraries you're compiling? That seems like it would be easier sometimes to just set up test parties everyone would have instead of exactly compiling the binary you want in the end.
The question is whether you have to use exactly the same binaries when you compile it again. And unfortunately, the answer is yes, you do. And yes, that does make it more difficult to use. So it's very much something that you might do at the very last stage of a release when you've got your code finally drilled down. That's the time when you might start using the profiling feedback. Of course, then you've changed your code, so then you have to test it again. These are parts of the reasons why it's perhaps not as popular as it could be, but it can be quite effective. I would like to make it more flexible so that that kind of approach would work more effectively, but there's nobody working on that in that area right at the moment. In front there.
How does pre-compiling improve performance?
How does which compiler?
Pre-compiled headers.
How do precompiled headers improve performance? Precompiled headers improve compilation time. So precompiled headers is a feature that GCC has had since I think around the 3.4 release. It was implemented by Jeff Keating at Apple. With precompiled headers, you can basically you can compile your .h files essentially, and then you're permitted to. You can only use one precompiled header per compilation, but it can be a very effective way of cutting your compilation time down by quite a lot. It was developed at Apple because Apple has this vast set of header files, many of which are included by every single application. So if you compile, all the Cocoa header files or something into one precompiled header, it can make your compile time, go down 40% or something like that. So it's a very significant benefit if you fit the profile of you only need one precompiled header. Most of your projects include the same header files. Yeah, there are no current changes planned for that. Dean, in the back?
Any plans for vectorization, auto-vectorization?
Are there any plans for auto-vectorization? Why, yes, there are. The Haifa lab of IBM has been working on auto-vectorization for several years now. It's actually implemented. If you use the -f tree -vectorize option, your code will auto-vectorize if you're very, very lucky. I've always been a little bit skeptical about auto-vectorization because it works mainly for scientific code, and I don't personally happen to be a scientist. But if you do write code which is very loop-heavy, especially Fortran code, let's say, and if your alias analysis is very good, this is a case where alias analysis is absolutely key. If your alias analysis can prove that your assignment to some element of an array is different from your uses of some element of some other array, which is something that's pretty easy to prove in Fortran, but it's pretty hard to prove in C, where you do not know where pointers point to. If you can prove those cases, then the auto-vectorization does work. This is useful for things like SSE or SSE2 on Intel chips or AltaVec on PowerPC chips. It will actually take your loops and just without any special effort on your part, it will turn them into loops that use the SIMD instructions, which have been added to modern processors. So, as I say, it works for very special cases, which mostly happen to be Fortran programs. You can write C programs which auto-vectorization works for, but most people do not write those C programs.
And just to get back to what you were saying about headers, are there other things going on to try to speed up compilation time for GCC?
The question is, are there other things going on to try to speed up GCC's compilation time? Yes. I mentioned the LTO project, the whole program optimization project. In order to make that work, we need to speed up GCC's compilation time. We need to speed it up in general so that it will speed up for the particular case of whole program optimization. And the approaches that we're using to speed up optimization time are primarily in the area of changing the internal data structures. It turns out that once you get beyond trivial programs, you can predict GCC's compilation time by measuring how much memory it uses during the compilation. So the way to speed it up is to make it use less memory, and also to make that memory be more cache friendly, that is, not to point all over the place. And so efforts are being made in both of those directions. I don't know how many non-compiler developers know this, but GCC actually has a garbage collector inside it, which is part of what it does. When you're compiling a very large program, I mean, you'll never see this unless you use the options which say, tell me about this. But when you're compiling a large program, GCC will actually run a garbage collector on its own internal memory structures. This is a convenient way to make it easy to write new optimization passes, but it has truly terrible effects on compilation time of large programs. So a lot of, not a lot, but a significant amount of the efforts to speed up GCC are also to take chunks of memory out of the garbage collector and into memory pools or various other memory objects that we have within the compiler. I mean, for those of you who are not compiler developers, you probably went to your compiler classes in school or not, but if you did, then they taught you about parsing and code generation. It turns out that actual compiler work on a real compiler has nothing to do with those things. A lot of compiler work has to do with managing your data structures. It's kind of like any other large program. And managing your data structures and learning how to traverse them rapidly and spending as little time as possible implementing your optimizations. It turns out that generating highly optimal code is much simpler than people think it is. It's just that when you actually generate perfectly optimal code, your compiler takes hours to run, and users find that unacceptable and they never turn on your options, and it's very disappointing. So you have to learn how to implement your optimizations so that they will run in an amount of time which people are willing to tolerate.
Speaking of taking forever to compile, the LTO seems like it will be very serialized and not really take advantage of multi-core processors very well. Is there any maybe incremental steps for keeping track of certain information about certain object files so that it doesn't have to be rediscovered every time the LTO runs?
So the comment is that LTO is going to take a long time, and in particular is going to be very serial and not take advantage of multi-cores. And the question is there any plans to cache the object file information in some way. And the answer is we haven't gotten that far. My hope, which is not being realized right now, but there's still time to change it, my hope is that it'll be possible to simply mmap the object file into memory and not do anything else. It'll just be ready for use. That's not the approach we're taking right now, but that may be the approach. Well, if I have my way, that'll be the approach we move toward in the future. I should also add that Ken Zadek, who's spearheading the LTO project, does have plans on paper for parallelizing it more than you might think. You can actually do things like say, oh gosh, this function's inlined in these 20 different locations, and then just parallelize the effort of doing the actual inlining and then come together at once. So yeah, that is, as you say, multi-core architectures are the wave of the future, and the compiler does need to learn how to take advantage of them. He's actually thinking of parallelizing it by shipping it out to different machines. This is not going to be in 4.4.
Does GCC collaborate at all with LLVM?
Does GCC collaborate with LLVM? Why? Are you from Apple? Let's see. I mean, well, the short answer is no, we don't. The longer answer is we do talk to Chris Latner quite a lot. Chris Latner is the lead developer of LLVM at Apple, and as you know, there are several other developers of LLVM as well, of course. We did discuss the possibility of actually incorporating LLVM into GCC at one point, but technically it seemed doable, but the legal issues turned out to be a problem. LLVM is owned by the University of Illinois under a reasonably generous license. GCC, of course, is under the GNU public license. The licenses were not compatible. We tried to persuade Chris to get Apple and the university to agree on some kind of license which we could use to incorporate the code, but that wound up not happening. In part, I'm sure there were legal difficulties I have no understanding of. And in part, I think that Chris felt that the GCC community was not quite as welcoming of LLVM as he hoped it would be. I mean, I like Chris Latner, and he's made excellent suggestions for GCC over the years, but at the moment, we don't have any plans to incorporate it directly. There's been talk about having GCC generate the LLVM bytecode representation to feed into the LLVM compiler, which is one feature of LLVM. I don't know if these things are going to happen. But it's a good question, and I'd like to see more cooperation. I just can't say whether it's going to happen. Apple has been pulling away from GCC to some extent. They've historically been a strong GCC contributor. They're moving much more strongly toward LLVM these days.
Is the whole program optimization stuff going to support libraries as well, such as libc?
Will whole program optimization support libraries? And the answer is yes, it absolutely will.
So if I find a security hole in libc, does that mean I essentially have to treat it like a static build and fix all my binaries? That's part of the function?
The question is, if there's a security hole in libc, do you essentially have to relink all your binaries? And the answer is yes. If you've chosen to take advantage of whole program optimization and then you find some such bug, then yes, you will in fact have to recompile all your binaries. So that's one reason you might not want to do it for libc. Depends on how performance sensitive you are.
With the improved alias support, are you looking at taking more static analysis tools into the GCC-based compiler?
The question is, with the improved aliasing support, are we going to be bringing more static analysis into the GCC compiler? That is something I would very much like to see. It's not something that's being actively worked on by anybody as far as I know. Well, let me take that back. There's a group called Global GCC in Europe, which is being funded by a coalition of some European governments who are working on improving GCC's static analysis. Unfortunately, they're taking an approach which I'm not sure is ever going to get back into the main line of GCC, although it may become useful as a tool by itself. They're taking an approach which is pushes the compilation time up enormously to the point where most people are not going to be willing to use it. For those who don't know, static analysis tools are essentially tools to warn about questionable cases in your program. That's the primary use of them. To say, oh, well, you're doing something here which looks like it might be bad programming style. Maybe you know what you're doing, but maybe not. So the compiler obviously has a great deal of knowledge that can be brought to bear on issues like that. But there's nothing going on other than global GCC that I know of.
Sort of follow up. Does the CIL intermediate language provide the aliasing information you need such that you could write better standalone static analysis tools using GCC to go through that parsing and discovery work?
The question is whether CIL has the information needed to do better static analysis, and my answer is I have no idea. Anybody know? Nobody knows.
A lot of the static analysis tools really want to see the source, not the intermediate, because there are language-specific things you need to worry about, and the intermediate languages are usually designed to consider that.
Any other questions? I think that's it. Well, thank you very much. That's a very good question.